second to try and kick a field goal, a 57-yard field goal.
Yeah, who could blame
So he challenged it, he won the challenge, so he got an extra second. But their kicker had been screwing up that game, so they put in their redshirt freshman who had only kicked 2 field goals in games before in his life, and had him to try and kick a 57-yard field goal with 1 second left.
57 yards.
And he did really well. He
got pretty close.
Yeah, it probably would have been like a 54, 55-yard field goal at least, but he fell short. Auburn guy caught it and ran it all the way back to a touchdown.
All the way.
Oh my God!
It was tied, by the way. It was tied. So we're going to go to overtime.
I did hear someone comment on Facebook. If you don't follow college football, you don't realize Alabama just exploded. The entire state of Alabama just exploded.
Yeah, there's high suicide rate now.
It was hilarious.
So the rumor I heard was that we may draw Alabama in our bowl game.
Alabama's king. That's the guy who almost got it.
It would just not even it'd be cute. We players running around.
Oh, it sucks so much. That's so brutal.
The next big game, baseball.
That sounds really
Calendar.
fun. I don't follow it. I don't follow baseball.
Baseball sounds like golf. That's kind of what I do when I play golf, is I chase it wherever it goes.
You like my kind
Not
of golf game.
That's awful. It's fun.
Spend more time chasing it than getting it the whole game.
My
I
brother,
like riding around the golf cart.
5 over 5.
my brother-in-law uses one club, a putter. He putts all the way down the green until he gets all the way down the course, not the green, but all the way down the course.
It's cheaper that way.
Yeah, large scale putt.
Yeah, per swing.
Does he drive with a putter?
Yeah, well, I mean, he tries.
No, drives.
He tries to
he
drive.
tries.
He tries to drive with a putter. It doesn't really go very far. Okay, so welcome back to our last week of class, and so I sent out an email giving you the option of taking the final exam 1 of 2 days, Wednesday of next week at 7 p.m. or Friday afternoon, 3 o'clock, I think it was. I sent out an email. You have the option. We'll do both of them in this room. So that's what we're going to do. Before that, you should take time to do the student assessment, and since some of you may not have, most of you haven't done this before, in every one of your classes, I believe, you are given the opportunity to assess the instructor and the course and the textbook and other things. So I think you connect to it from Blackboard. Never done it as a student, so I'm not sure, but I think that's how you do it. So there's some standard questions on there about, and there's some numerical things, but then you have the opportunity to kind of free-form answers at the end. I read all of them, and I really do value the opportunity to read comments from the students. It's all anonymous, right? At least, except for when there's one student in the honors section, then it's just kind of hard to be anonymous. But you know, what can I do about it? Okay, so I would still value Mr. Vestal's comments. In order to encourage you to give your comments, I will give extra credit. If more than 80%, so how many? We have 16 students, 80%, what is that? 8% of, yeah,
Is
14.
that calculated independently between honors and non-honors?
100% of the honors.
Oh, that's easy.
Yeah, I guess we'll have to exclude Mr. Vestal. So. No, we should let him do it. You know that I know who you are, so that if you want to, I don't know how to solve that problem, so I don't have any way of doing that. But if you want to help participate to raise the participation rate.
Signs in on one of ours, and then one of us at random that you don't know signs in and does it on his.
I guess you can do that. I don't mind. I don't. That's okay with me. I think it violates all kinds of other rules that you've agreed to, but it's all right with me. So if I get it, I want at least 14 students. 13. Is it 13? Thank you. 80%, 13 students responding. Then I will give extra credit homework. 1 extra credit homework for everybody in the class.
So everybody but one person.
Everybody gets the extra credit. All right. No, there's 16 students in the class.
Oh, no.
Yeah. So if at least 13 of you respond, and then I'll give extra credit to everybody in the class. And that's because I do want to see your comments, and I do my best to make them anonymous. Okay. So and I do read them carefully. I have done this every year since the beginning. For me it's good feedback, and I do show them to my department chairman and the dean when the dean asks. I don't know if this dean will ask, but anyway, I think it's good for them to see comments and stuff as well. Okay. So any questions about that? Everybody know how to do it? Please do it. Oh, I should give a date here. How about by this Friday, by midnight Friday? Okay. By midnight Friday. What is that, 6th? Okay. So, all right. Now, we're on to the subject of gravity. So, first interesting observation. So I'm going to give you a few interesting observations. If the Earth is spherical, as we usually assume it to be, then the force on an object outside of the Earth, out here, because of the influence of the Earth on the plana and the propagation through the plana, and then the plana acts on the second body, the force on that body will be directed back towards the Earth. The product of the two masses goes like the inverse square of the distance from the center of the Earth. R is here. And the two masses are M1 and M2. Okay. Notice that that doesn't depend on the distance from the surface of the Earth. It's from the center of the Earth. If we compress the Earth into a smaller sphere, keeping it spherically symmetrical, same mass, just smaller radius, it doesn't affect the force that the Earth exerts on that second object. It doesn't alter it. It's kind of interesting. If we expand the Earth and keeping the same mass, so now the material has been stretched out, rarefied, it's less dense, and it's just below, so it's just below the object there. The object is just above the surface of the Earth now. Doesn't change the force. The force is the same. It's not been altered by these strange things that we've been doing to the Earth, as long as the Earth is spherically symmetric. This was observed first by Newton, proven by Newton using the calculus, and the proof is similar proof is in the textbook, which you can go over. We're not going to go over it we're not going to go over the proof here in class, but you can read it in the textbook. It wasn't something he understood right away, but it's an interesting thing, in fact, that you could consider all of the mass of the Earth to be concentrated at a point. As far as the motion of that object, as the second object is concerned, it doesn't matter, as long as the mass of the Earth is the same. And so, in other words, you can consider point-like objects when you're considering the point-like planets and suns and things, when you're considering the orbits of the planets around the sun. Interesting observation. As long as the body is spherically symmetric. Now, if you relax that caveat about the symmetry of the body, then things start to change, and it's no longer true. So how would you make it not spherically symmetric?
Put a really heavy city on one point.
Sure. Yeah. Heavy city.
Rocks.
Yeah, put rocks and things, you know. So the Earth doesn't have a spherically symmetric radius, right? I mean, it has high points and low points. Okay, that will introduce some variation in the force. That depends on where you are in the orbit. That's a very small amount for the Earth. The deviations in altitude from the surface of the Earth are not significant enough to make that much of an effect, but it does exist. If there are dense places here, there may be, for some reason, much more dense material under some part of the Earth. It will have some effect also. It causes deviations from that. But it certainly simplifies the fact that the Earth is almost spherically symmetric, and these effects are negligible. And that makes it much easier to understand the motion of the Moon around the Earth, or the Earth around the Sun, because the Sun is almost very spherically symmetric compared to the Earth. Makes it a lot easier. Of course, now if we have a second planet out here, we have a second body out here, or third one, make it a third one. Now things get more complicated. We have a three-body problem. Every pair of bodies exerts a force on each other that are equal and opposite in magnitude, and so now it gets to be much more complicated. In general, there's no general solution to this problem. We know special cases, but in general, there's no solution to this general three-body problem in gravity. Okay, so it's kind of interesting that the one that was easily solved is which is spherical symmetry around the Earth, and the Sun is spherically symmetric, and watching the motion of the planets around the Sun turns out to be actually tractable problem, and so it was one that was solved. By the way, everybody I think probably knows the news about ISON. The comet is a goner, right? Oh well, it's a disappointment. After I hyped everybody up at Thanksgiving, go out and watch it. There was nothing. Okay. Now, suppose that you are. Let's consider some circular orbits. Suppose that you are in orbit around the Earth. Actually, suppose that the space station is in orbit around the Earth, and that you are trying to catch up with the space station, and that's a circular orbit here, in case you don't know that. And this one, you are also in a circular orbit, same radius, and of course, therefore, you have the same velocity, right? You have the same speed. So the space station is traveling around that circular orbit. You have the same speed. Why do I know that you have the same speed as the space station?
If you didn't have the same speed, you wouldn't stay in orbit. You'd be pulled back down.
Different kind of orbit.
Right.
Yeah, it'd be a different kind of orbit. Right. Okay, so let's look at this one then. I'm behind. You can see the space station out in front of you, and you want to get to it and dock with it. What do? Well, if you fire your rockets in order to go that way, what will you do instead? You'll start going up this way, right? Because if you fire your rockets behind you in this instance, you will actually inject yourself into an elliptical orbit. And this will be the low point of the elliptical orbit. So the ellipse will look like this, possibly, depending on how long you fire your rockets. And when you get back to that point, the space station will have gone around even more than once, because the period will be quite a bit shorter than your period. So in fact, you will have ended up farther behind rather than closer. So it kind of messed things up. Okay, now what do? So that didn't work. How do you actually...
Could you just wait? Could you just keep falling farther and farther behind until it comes up?
Well, you're not falling behind. You're keeping up. Oh, you mean go into this elliptical orbit.
Yes.
If you timed it just right, I guess, you might be able to time it so that you got an elliptical orbit that was just right, so that
Eventually,
16 orbits later, the space station is in the right place, maybe.
Do you shoot downwards?
What if you were to shoot downwards? What if you were to aim towards the Earth?
Well, not directly.
Not directly. Okay, somewhat downwards. Okay, somewhat downwards. Okay, so but as long as you're increasing your angular velocity, you're going to be going into more of an elliptical orbit. So there's let's see. Yeah, you're still going to have the problem of creating an elliptical orbit. It's a difficult problem, and it takes more than one firing. You can't do it in one firing. It's going to take more than one firing. When Apollo 11 was preparing to land on the moon, Buzz Aldrin, who was the second man with Neil Armstrong, the two of them went down onto the moon. He had specialized in figuring this out because he was the one responsible for docking, going back up to the command module when they got back up. So he studied this problem, and they called him Dr. Orbit, I think was the name. His nickname was Dr. Orbit because he knew exactly how to do this. It was not an easy thing to do. Yes, sir?
Would something like using the rocket to speed you forward, but using a second rocket to correct the change in orbit be possible?
So the net force is what you're looking at, right? So if you have when you mean a second rocket firing at the same time, so then there's a net force, and that's really what you're looking at, is what is the net force that you're looking at. So even if you have two rockets firing simultaneously, it's the net force produced by the two that's what you're considering. Okay?
So gravity lied. Gravity the movie lied.
What was that?
Yes.
Gravity
They had debris going much faster than the non-debris, but kept hitting it over and over again because it was on the same orbit.
If it's in the same orbit, then it would have the same velocity, independent of the mass of the object. Right.
They were small debris.
I was thinking about how like they would aim for a space station and they'd like point themselves directly at it and then just like shoot their thrusters.
Yeah. Now, obviously, you could do that for a short time as long as you can hook hold of it quickly, right? But you're going to start diverging, and you have to be able to. And I'm not sure of the details of this. Can you catch up before you start diverging? And that's the problem. It's obviously not a good situation to try to dock in where your time is so short that you don't
Just turn around.
Turn around and go back down. Okay, so the same thing happens then on the trip to Mars. Suppose we are going to Mars, and we have then, as you can read in Chapter 9, he goes through this problem in the trip to Mars, the planning for the trip to Mars, the Earth's orbit and the Martian orbit. And I'll show you this tomorrow, Wednesday, on the interactive physics software. How do you go from the Earth to Mars and then back again? So the most economical process in terms of fuel is called a Hohmann transfer. And the Hohmann transfer does, as we just proposed, we fire forward with our rockets, and that produces an elliptical orbit, and you do it just so much that the maximum distance from the Sun matches the Martian orbit. And if you keep going, if you don't do anything at that point, you just fly by Mars and go home, right? As long as you don't get trapped in the Martian gravity well. So you fly by and go home. Now the problem is the Earth won't be there. When you get there, it will be some other part of its orbit. So the timing is kind of messed up. But at least you get close to the Earth that way. But then if you decide that you want to land on Mars, then you obviously you have to time all this. So Mars would be there at the same time, right? So where it is in its own orbit depends on, you have to time your leaving the Earth's orbit to reach the Martian orbit here. And then you can land on Mars, and then to go back, now once you get out of orbit from Mars, you're in the almost circular Martian orbit around the Sun. Then you have to decelerate, fire backwards, and that will bring you down into again, an elliptical orbit where the minimum distance now matches the Earth's radius from the Sun, and then you can, if the timing is right, be there when the Earth is there and land on the Earth. So this is the most economical transfer method, the Hohmann transfer, and it's most economical in terms of fuel. It's the most fuel-efficient means of getting from Earth to Mars, but it could take some time. It's not the most efficient in terms of time, transit time. He discusses all this in Chapter 9, and it's an interesting read. There's just enough technical detail. You can kind of put all this stuff that you're learning in Chapter 8 to use in Chapter 9. Makes an interesting thing, and that would have been on our reading, but we're not gonna have time to do this. But it's kind of neat. Okay. Now, and the same thing happens. Same thing could be considered if we are standing on the Earth. Here we have a cannon on the Earth, and we're going to fire the cannon that's on the tower like this, or you're just holding a gun and you shoot like this. What is the trajectory of a bullet? Well, now in our previous homework, we had done that this was a parabola, a parabolic arc. But that assumes that the force of gravity is perfectly the same, exactly the same. And the correct trajectory is not quite a parabola because gravity is getting stronger as the bullet falls. But the correct trajectory of the bullet is what? If it didn't hit the surface of the Earth, if the Earth were concentrated at a point here, what would be the trajectory of the bullet? It would be an ellipse. Yeah, so there's this implied ellipse like this, and if it could keep going, it would come back and hit you in the back of the head. Right? With the center of the Earth, that's the concentrated Earth that is compressed into a small sphere at one focus of the ellipse. Okay. Now it doesn't do that, of course, because it hits the Earth. Even if it could penetrate the Earth, gravity is now going to be altered. Once you're inside of the Earth, gravity is now altered. And so what is the force law if we actually allowed the projectile to go inside of the Earth? In fact, let's consider the following problem. What if we dug a tunnel through the Earth? Narrow tunnel. And we take the ball, hold it above the tunnel, and let go. Now, as long as it's above the surface of the Earth, neglecting that this tunnel makes this Earth not spherically symmetric anymore, but okay, it's a tiny little tunnel, so that we're not going to have much effect from that. We let go. So above the surface of the Earth, it's still 1 over r squared force law. That is, as long as it's out here, the distance from the center of the Earth, the force goes like 1 over the square of the distance from the center of the Earth. But now once we get inside, so this is r greater than the radius of the Earth, what happens if we get inside the radius of the Earth? How does the force vary then? Does anybody know?
You can't count anything on top, right?
Right, that's the interesting thing. So, in fact, if we're at this location, we would figure out how much of the mass of the Earth is inside of that sphere, a sphere of that radius r. Okay. Now, in proportion, it will be in proportion to the radius, right? So it will be r, it would be r, this fraction of the mass of the Earth will be inside of that sphere. If we draw an imaginary sphere of radius little r, we'll have an amount which is proportional to little r cubed over big R cubed times the total mass of the Earth. This is how much mass is inside of this imaginary sphere. Yes, sir, Mr. Flanagan.
Would you have to take into account that the mass that's now above you would be pulling you up with gravity?
Well, actually, if you have a hollow sphere, let's consider what let's suppose there is no mass inside of that sphere. All the mass is inside of a shell. So you're inside of a shell. If you're inside of a massive shell, what happens? There is no force. There are forces acting, but they all balance. So there's no net force on you inside of a hollow shell, as long as it's spherically symmetric. That's the complementary part to the 1 over r squared force law outside. So if you're outside, all that matters is the mass inside of a shell, inside of you, inside of your distance. If you're inside the shell, the force is actually vanishing. All the forces balance. You get just as much pulling you up as pulling you down from the other part of the shell. That's peculiar to the 1 over r squared force law. Peculiar to something like gravity. Electrical forces do this as well. as long as the force, the natural force, goes like 1 over the distance, square of the distance, then you'll have this funny balancing act that happens. If you're inside a spherical shell with charge on it, and you have charge on you, same thing will happen. If you're inside, all the forces balance, and you're weightless. You just float around. If you go outside, then there's either attraction or repulsion depending on whether the charges are the same or opposite. It goes like 1 over the distance squared. It's a remarkable fact, and it pertains only to the forces that are 1 over r squared. There's gravity and electric force. Okay, so now the total mass inside of the imaginary sphere goes like little r cubed. And then so the force inside is that mass divided by r squared. So it goes like r cubed m over r cubed, but divided by r squared. So the force inside is proportional to the distance from the center of the Earth. And it's directed towards the center of the Earth. What does that look like? I should, let's see, there's a G here, and then the mass of the body. So we have a G and M here as well. What does that look like, though? Yeah, it's like a spring, isn't it? It's a simple harmonic oscillator. The force is proportional to the distance from the center of the Earth. This little r. So it's going to oscillate. So if we reach in and start it just below the surface of the Earth and let go, it'll act like a simple harmonic oscillator, oscillating back and forth like that. And what's the frequency of the motion for a simple harmonic oscillator? This is like a spring constant, isn't it? This piece is like K, like the spring constant. What's the frequency of a simple harmonic oscillator? Where we have a spring constant K, and the body has mass M. That should be on the
M over K?
square root of K over M. And now K here is the effective K. There's not a real spring there, but it looks like a spring constant. So that would be Gm over r cubed.
No little m?
No little r.
Little m.
Little m. No little m. The little m cancels. There's a little m up here and a little m down there, and it cancels. So it doesn't depend on the mass of the object that's doing this. And in fact, you can compare this to and so you can get a period out of this, right? The period of motion, how long it takes to go down to China and back up here is 2 pi over omega. So it's 2 pi times. This is very close, very resembles the period of motion. Let's consider a circular orbit around that same Earth. How long does it take if I shoot it fast enough? It keeps falling, but the Earth, in some sense, keeps falling under it. Right? It follows the curvature of the Earth. So I can create a circular orbit at 3 feet above the Earth as long as there's nothing in the way. As long as it doesn't run into anything, and as long as there's no air to slow it down, nothing else. Right? It would just skim across the surface of the Earth at 3 feet above the surface of the Earth, go all the way around the Earth. How long would that take? All right, remember our relationship, right? The force provided by the Earth has to balance the force required to keep an object in a circular orbit of radius r, speed v, or we could write it in terms of omega. Oops, r squared, excuse me. Okay, let's cancel the masses here. And the period here is going to be Gm over, and this should be big R. That's the radius of the Earth here. R cubed square root. Does that look familiar? Frequency is gm over r cubed. The angular velocity. The period is 2 pi over omega. 2 pi root r cubed over gm. Oh, did I mess that up here? Yeah, right. They're both the same.
So if you drop something into a tunnel and shot something really fast 3 feet above the earth, they would return to you at the same time?
Right.
Well, that's slack. That's clear. How does that you can't, if you jump and then it
Isn't that cool? Okay, so in case you want to convince yourself again, go through this argument, and you can figure it out. This is involving the only physics that you don't that's new here is this part here where the force inside is proportional to the amount of mass inside of that sphere. That's the only part that's new that you haven't seen before. The rest of this you've seen before, and you can piece this all together. So I have to figure out how much mass is inside of the imaginary sphere, and that was the part that was new here. That's the part that you might have to think about.
But that's constantly changing as you fall.
Yeah, that's right. Right. It's changing. In fact, like the cube of the distance from the center. But the force is going like 1 over the square of the distance, and so the net effect of those two competing effects is that the force will decrease linearly with the distance from the center of the Earth.
Exactly like it would for the spring.
Right.
The force is decreasing, but it's still got its momentum. It's going to bounce to the other side. It's going to pull it back.
Right. It's exactly the same. Isn't it interesting? Okay, and in fact, it has the same period of motion. What a coincidence. It's an amazing coincidence. Okay. Anyway, work through this. Just so that you can see, really, you understand all of this parts of the physics. The only thing of it that's new to you is that part that I said that as long as we have a spherically symmetric mass distribution, then the force on a body outside depends only on how much mass is contained inside of the imaginary sphere. So that would be true as long as you have that uniform mass distribution. That's the only thing that's important here. Okay. So let's consider how we can analyze this a little bit more easily. Let's go to polar coordinates. And let's consider the motion of a body using polar coordinates. Now, the first thing you need to recognize, why can we get away with polar coordinates? So why is it that a body, if I start it moving around a center of gravity like the sun, it moves in a plane? Well, what else could it do? Well, it might wander around like this. Why doesn't it do that?
Because that's not the direction of force.
Okay. So let's consider here there's this body moving like this. And here's the center of gravity, which is exerting a force in this direction. Okay. And in fact, and I've drawn it in a rather convenient situation there, and it's a little too convenient. Because it doesn't necessarily have to be quite like that. It could have started off, could be like this. Okay, here's the velocity and here's the force. Okay, oops, that's the velocity. And the force is radially inward, always pointing towards the center of gravity, the center of the source of gravity. Okay, so this radius vector and the velocity vector define a plane. So if we have two vectors, what is the direction of the plane? Can we use vector multiplication to define the plane of two vectors?
R cross V.
R cross V. R cross V is perpendicular to the plane defined by the radius vector and the velocity vector. So let's suppose we start some body off here some velocity. We give it a velocity this way. It's some distance from the sun. We start the Earth moving like that. Okay, does anybody recognize that thing? Arc cross V?
I like the circular motion.
Yeah, we saw it in the thing on circular motion. And what is this? Arc cross V. I multiply it by the mass, so it becomes arc cross P. That's the angular momentum vector. Okay. Oh yeah, R cross P. So the angular momentum is perpendicular to the plane formed by R and V. Now, this force is directed radially inward. So what happens to the angular momentum? The torque is R cross F, but F is directed back along R. So what about the torque?
Zero.
There's no torque. The gravity exerts no torque on the Earth. And we're talking about gravity from the sun exerts no torque on the Earth. So what does that mean about the angular momentum?
It remains constant.
Angular momentum is a constant. It's constant both in magnitude and direction. So if this V were somehow to come out of the plane, what would happen to the angular momentum? If V somehow at a later time came out of the plane, then the angular momentum would be in some other direction.
We'd just have a new plane.
We'd have a new plane. The fact that L remains constant in direction means that the planet has to orbit in the plane. So the orbiting in a plane is an expression of the conservation of angular momentum. L as a constant means two things. First, the direction of L constant means that the plane, the orbit, must be in a plane. That we get simply from angular momentum, and that the force is radially directed along back towards the sun. Any central force, this is called a central force, meaning a central force is one that's either radially inward or radially outward, will conserve the angular momentum, and the orbit will be in a plane. Okay? All right, so therefore, if it's going to be in a plane, let's use polar coordinates to describe the motion. Okay, so now let's go back to this problem here. We have R, and we have R is the distance, and then the unit vector. So the position of the planet is described in terms of the distance from the sun and an angle with respect to some fixed direction. And this all takes place in the plane of the orbit. So we have now acknowledged the fact that the Earth will move in a plane around the sun and is not going to move out of the plane. It's going to move in the plane. Okay, and remember from our exercise using polar coordinates, we take the derivative of this with respect to time to get the velocity. And so we get this piece here, plus we get the r times the derivative of r hat with respect to time. And just to review that, the derivative of r hat is a function of theta, and theta is a function of time, so we can use the chain rule, the r hat d theta times d theta dt. D theta dt is what we call theta dot, and r hat, the derivative of r hat with respect to theta is theta hat. So the velocity has two components. One is radially outward, which is r dot, and the other one is in the theta hat direction, the angular direction, r theta dot. So, having done that, what is the square of the velocity then? Remember, r hat and theta hat are perpendicular to each other. So what is the square of the velocity?
R dot squared plus r squared theta dot squared.
Good. It's just like the Pythagorean theorem in that sense. Right? That r hat and theta hat are perpendicular to each other. If you form the dot product of v with itself, these cross terms will vanish. And r hat dot r hat is 1, theta hat dot theta hat is 1. So that's the square of the velocity. Okay, so in polar coordinates, the kinetic energy is 1/2 mv squared, or that. That's the kinetic energy expressed in polar coordinates. And how about the angular momentum? It's mr cross v. So we have mr r hat cross r dot r hat plus r theta dot theta hat. We get two terms here. We get mr r dot times r hat cross r hat, and then we get mr squared theta dot r hat cross theta hat. One of these terms vanishes. Which one goes away?
R cross R.
Right. Any vector crossed into itself is 0. And r hat cross theta hat is coming out of the plane. We could call it the z direction. So the angular momentum is out of the plane, and it has a magnitude, so z hat meaning it's out of the plane and has a magnitude mr squared theta dot. So that's the angular momentum vector in polar coordinates, and its magnitude is mr squared theta dot. Okay, and that's a constant. The angular momentum is a constant in magnitude. So I could rewrite the kinetic energy, and here's an interesting step here. It's going to lead to something interesting. 2mr squared. Let's see, r squared, l squared. Yes, that's right, 2mr squared. Yes, right, good, that's correct. Okay, now is the total energy conserved? Angular momentum is conserved. Is the total energy conserved, meaning the sum of kinetic and potential energies? Right, because gravity is conservative, even away from the surface of the Earth. So what is the potential energy of the force? Goes like gm little m over r squared. What is the potential energy for that? So we haven't done integration yet. We'll do that beginning of next term. But remember that the force is the negative derivative of the potential with respect to position. And so I can give you then show you that this does satisfy that. If I take the derivative of this with respect to r, I get the force goes like 1 over r squared. So the potential energy goes like gmm over r for the Earth orbiting around the Sun. And we said that the total energy was conserved. And so then all of this gives us, with a little bit of work here, we've gotten finally to this expression, which would be very interesting and very helpful to see how all of these orbits work. It's very interesting to see this gives us a little bit of monkeying around with the equations. We've come to something that's actually very, very helpful and interesting. Okay. Now remember the origin of these two terms. Those were two pieces of the kinetic energy. One was the angular part of the kinetic energy. The L squared over 2mr squared is actually kinetic energy. Right? This was originally kinetic energy. But I'm going to play a game. I'm going to say, suppose we were to invent a non-real system, an imaginary system, whose potential energy, this was the original potential energy, PE. Let's suppose we invented an imaginary system whose potential energy and kinetic energy were different. So suppose we had something that looked like 1/2 r dot squared, 1/2 m r dot squared. Well, that's like something moving along in one dimension, 1/2 m v squared, right? 1/2 m v squared. Well, this is just the radial part of the velocity alone. And let's suppose we're going to invent what's called an effective potential, which is all the rest of it here. This effective potential is then two parts. It's this piece, which really is kinetic energy, but I'm going to be imagining that it's potential energy. So now I've reduced it to a one-dimensional problem. A one-dimensional pseudo problem. It's not, there's no physical system that's exactly this way, but mathematically it resembles the same thing. Okay, let's plot that effective potential. Let's plot some different effective potentials we have known, in fact. But yeah, let's plot a few of them. We have a few potentials we have known. Really, we have two. Let's go back and look at some of the potentials we have known. Potential energy above the Earth, surface of the Earth, if you're near the surface of the Earth. Gravity near the surface of the Earth. What does that look like? Potential energy. It's just a function of the height, right? mgh. How about the potential energy of a spring? Function of x. Good, 1/2 kx squared. Almost, yeah. You're remembering the force.
Very wrong.
Yeah. Now you're close.
Thanks.
You're remembering the force. Remember, the force is the negative of the derivative. The force is the negative derivative, so it's minus mg here. The force here is minus kx, right? So I'll take the derivative to get the force. Negative derivative to get the force. Okay, so let's draw those. I'm gonna draw some pictures here so we can see what these look like. A little bit more space here. Okay, here's the potential energy above the surface of the Earth. This is near surface as a function of h. Straight line. Doesn't do much. How about a spring? Well, it's a parabola like that, 1/2 kx squared. Okay. And at h equals 0, you hit the surface of the Earth, so it can't go below 0. So let's imagine, and remember the total energy, the total energy is a sum of kinetic plus potential. So if I draw a line across here and say that's the total energy, then what lies below this is kinetic energy between here and the potential energy, right? This would be the amount of kinetic energy. So where's the kinetic energy the most? It's right when it hits the surface of the Earth, right? And it's the least right at the top point of its motion when it hesitates, that instant of time when it stops moving up before it starts moving down. Okay? So if you draw this line here, you can get an idea of the kind of motion, just qualitatively. That as it's going up, its kinetic energy is decreasing until it comes down. Kinetic energy gets to be 0, and then it comes back down. Kinetic energy starts increasing, trade-off with potential energy so that the sum is the same. It's that horizontal line. Okay, so you get the idea that just before it hits the floor, it has the most kinetic energy. How about the spring? Same sort of thing here. The kinetic energy is what remains under the total energy. Out here, we have no kinetic energy at the very beginning of motion. When we pull it out, we let go of it, it starts moving inward, starts gaining kinetic energy, losing potential energy until it crosses the origin, and now it starts to lose kinetic energy until it reaches another point there where the kinetic energy has gone to 0, and now it starts moving back. So you can understand the motion that we've studied before. This is just a simple energy diagram, and this place where the mass reverses direction is called a turning point. In a simple harmonic oscillator, there are 2 turning points. And the mass moving above the surface of the Earth is just one turning point. It's when they get that hesitation here, and then it starts to go back down. Of course, when it hits the Earth, that's not really a turning point because of gravity. It's a turning point because it hits the floor. Okay, so we can study the motion from these sorts of energy diagrams, and so that's what I'm going to do with this very simple effective energy. Let's look at the potential energy due to gravity alone. The effective energy is L squared over 2mr squared. The effective potential energy looks like this. And so it depends on L. So let's set L equal to 0. If L equals to 0, then the effective potential just is the potential due to gravity. And what does that look like? What is that potential energy 1 over r? Negative 1 over r. What does it look like on this graph?
Are we graphing with respect to r?
Graphing with respect to r, thank you. So far away it goes to 0. And then as it comes in, it's just a little below the horizontal line there, just a little below the axis because it's slightly negative. And as it gets in closer, it becomes more negative until, as it's approaching the origin, it becomes really unbounded. So it looks like this. That's what the potential energy would look like. Okay, and so let's imagine that we have some object here. Can you see this yellow? Ugh, not too good. Let's try green. Let's suppose we take some object here and we fire it upward from the surface. Now let's drop it from that point instead. Don't make it. Let's just drop it from this point here. Okay, so we're going to start it here. It has no kinetic energy, so it's starting from rest, and we just let go, and it just falls, right, until it goes into the sun, or whatever's causing the gravity. Okay. So the kinetic energy would become unbounded, and just as it's approaching whatever's providing the gravity. Okay. So that would be the total energy curve here. Let's suppose we shoot from the surface of the Earth. So this is the surface of the Earth, and we're starting at this point. We need to give it, if we wanted to move away from the Earth, we'd have to give it enough kinetic energy. We'd have to give it this much kinetic energy in order that the total energy is 0. And then it would just barely escape the Earth. That would be the escape velocity of a rocket launched from the surface of the Earth straight up. Okay, but that's the potential when we get L equals to 0. In other words, it's not orbiting. It's got no angular motion. It's just moving straight up and down. Now let's give it some angular motion. Let's set L not equal to 0. So this is L equals 0 piece. If L is not equal to 0, then we have this positive L squared over 2mr squared. And that will change the potential. It will look like this. So this is L not equal to 0. This is that positive 1 over r squared pushes it away from the origin. Some people call this the centrifugal barrier. It's not really. It's due to the kinetic energy piece of the kinetic energy. It has to do with the angular momentum, the angular motion. Okay, but let's suppose we give it some energy here. Let's suppose we give it just enough energy that it's living at the bottom of this potential energy. What does something do if it's at the bottom of the potential well?
It stays.
It just stays there. It does nothing. So r doesn't change. This is as a function of r. So what kind of orbit is it where r doesn't change? It's a circular orbit. There's the circular orbit that we studied before. Just disguised. It doesn't look like the thing that we were dealing with before, but there it is. Now let's give it a little bit of extra energy. Give it a little bit higher energy here. It has 2 turning points, where the total energy crosses the potential energy curve. Those are turning points. It has 2 turning points, one closer and one farther than before. So, and that would be obtained by firing our rockets. We point our rockets straight away from the